All right, Honors Chem, today we are going to use our newfound knowledge of enthalpy, and we're going to start learning how to calculate whether reactions are spontaneous or not. And this, we're going to start off with a reaction that we all know fairly well: solid ice or solid water, right here, melting to water, liquid water. Now, the question here is, does this happen spontaneously? Does ice melt spontaneously? So let's think about this reaction. Let's think about this in terms of enthalpy. If I go from solid water to liquid water, is this reaction endothermic or exothermic? Do I need to put energy into this, or is energy released? I need to put energy into this. This is an endothermic reaction. I have to heat that ice up in order for it to melt. So is that spontaneous to have to put energy into that? No. Because my delta H here is positive, this part is what we would say not or non-spontaneous. Okay? Let's think about our entropy, though, not our enthalpy, but our entropy. As I take that ice from solid to liquid state, do I increase the chaos of the system or the disorder of the system? I sure do. Liquid is a lot less orderly than solid. So if I'm looking at delta S, or my entropy, I definitely am creating more disorder. So my delta S, why does this keep coming up on me? My delta S is very much spontaneous because I am creating more disorder. So this is spontaneous. Okay, so the question then becomes, which one rules out? One of those processes is spontaneous and the other process is not. So which takes over? Doesn't it depend on the temperature? Okay. We all know that at room temperature or above zero, ice does melt spontaneously. But at temperatures below 0 degrees Celsius, it does not. So a lot of times when we have the entropy and the enthalpy kind of battling it out, it really depends on what temperature this reaction is happening at. So here we go. Temperature has to be considered when determining whether a reaction is spontaneous or not very often, okay? So this is our equation. This is the Gibbs-Helmholtz law of free energy. So the free energy of the system is equal to the enthalpy of the system minus the temperature multiplied by the entropy of the system. Now, we know how to calculate delta H. We've done this before. We kind of know how to calculate delta S. We know the, products minus reactants. I'm usually going to give you the delta H and the delta S. So really, you just have to put it together. You're not going to have to calculate from scratch, okay? So the thing that we have to be worried about, though, is our temperature. Our temperature is given in Kelvin, okay? Temperature is in Kelvin. Now, Kelvin is a scale that we haven't really used a lot. So if I want to calculate Kelvin, it's the Celsius plus 273 degrees. And notice in Kelvin, we do not have this little degree or this not sign. It's just a big capital K. Okay? So Kelvin, if just a reminder, is based on the idea of absolute zero. So when we are at 0 Kelvin, we are at absolutely no kinetic energy at all. All motion of all molecules, particles stops. Okay? So here we go. Let's talk about our values of delta G, or Gibbs free energy. If our value for delta G is greater than 0, meaning it is a positive number, I'm sorry, I don't know why this is doing this. If we have a positive number, that means that the reaction will be non-spontaneous. Okay, so positive delta G, not spontaneous. Okay, if our delta G of the reaction is less than 0, meaning we have a negative number, that reaction will be spontaneous. Okay, so we're going to consider our earlier example. We have water. Oh, it looks like my power cord has gotten dislodged. We have water that is at 20 degrees Celsius. Okay, so the first thing we have to do is figure out what 20 degrees Celsius is in Kelvin. So remember, to figure out Kelvin, we take Celsius and we add 273. Okay, so 20 plus 273, that means our Kelvin temperature is going to be 293. Okay, and we are going to use this equation where delta G is equal to delta H minus the temperature multiplied by delta S. Okay, so I've already figured out the temperature. So I'm going to put that here. So I have a temperature of 293 Kelvin. Now, I plug in the delta H right here. I have 6.01 kilojoules. Now, it's really important that we make sure that we have things in the same unit. Okay? Notice our enthalpy, or delta H, is in kilojoules, but our entropy is in joules. We need to make sure our entropy is also in kilojoules. So I'm going to move my decimal place over 3 places. That way I can have it in kilojoules. So my kilojoules of my entropy is 0.02199 kilojoules per mole per degree Kelvin, and this is kilojoules per mole. Okay, so if we want to really be paying attention to our units here, notice my degrees Kelvin, or my Kelvin, cancels out. Okay, so I would have delta G is equal to 6.01 kilojoules. And then if I multiply this out, 293, let's see. .293 times 0.02199 gives me 6.44. Kilojoules with our sig figs. So 601 minus 6.44 gives me an answer of delta G being negative 0.43 kilojoules. Okay, now I only did to the 100th because these values only go to the 100th. Okay, now when we look at that, we do indeed have a negative sign, which means at 20 degrees, this would be spontaneous. And this is what we would expect. 20 degrees is roughly room temperature. We would expect that ice to melt. Okay, now let's check this out for negative 20 degrees. We're going to do the same thing, same equation here. We still are going to have the same delta H and the same delta S. What's going to change, though, is the temperature. So our temperature is going to be 273 now minus 20. So our temperature is now going to be 253 Kelvin. Okay, so we're going to plug this in once again. Delta G is equal to delta H minus T delta S. Okay, so when we plug this in, we're going to have 601 kilojoules for our delta H, 253 for our T, and 0.02199 for our delta S. Remember, our delta S and our delta H both need to be in kilojoules when we do this. Okay, and my computer doesn't seem to want to be working right now. So let's give it a minute. Hopefully it won't take too long. I'm sorry. Just skip over it until you can see me writing again, okay? Okay, here we go. Delta H minus T delta S, and here we go again. Hopefully this one won't be as long. Okay, so our delta G is going to be, we're going to have a positive 6.01 kilojoules minus 253 Kelvin, and then we're going to bracket this, multiplied by 0.02199 kilojoules per, this is per mole as well, per mole Kelvin. So our Kelvin cancels out and we're left with kilojoules per mole, which is what we wanted. Okay, so we're going to multiply this out. Okay, so 6.01 minus the quantity 253 times 0.02199. We get a delta G, or Gibbs free energy, of positive, let's see, with sig figs 2, we can only go to the 10th. We get a positive 0.44 kilojoules per mole. Okay, so that is a positive. So we know that this is not spontaneous. And we would expect that. At negative 20, that's below freezing, right? We would expect that ice to remain ice and not to be in the liquid state. Now let's do this same calculation for 0. I'm going to do it over here on the side. So delta G is equal to delta H minus T delta S. So we still have the same delta H. 0 is going to be 273 for our temperature, minus 273 multiplied by 0.02199. Okay, so we get we get 0.006373 kilojoules, which is really 6.73 joules, which is essentially zero. That's hardly any energy at all. If you really want to refine that even more, the true Kelvin truly is 273.15 plus degrees Celsius. But I don't expect you to memorize all those significant figures because 3 significant figures is plenty. Okay, so here we go. Let's determine the reaction spontaneity for this process. We have a delta H. Oh, and by the way, I should mention this as well. When delta G is 0, that means that reaction is at equilibrium. So at 0, isn't 0 our equilibrium between the solid state and the liquid state? So notice how close that was to 0. When we can get delta G to be 0, that is the equilibrium condition for that reaction. So that is a good way of figuring out what that equilibrium temperature is for a reaction as well. Okay, especially phase changes. Number 8, determine the reaction spontaneity for this process. Okay, so once again, we're going to set up the same equation. We've got it at 382. I think this happens every time I touch the screen with my hand, with the side of my hand. I think that's what's going on. Okay, so we've got our delta H right here and our delta S. Notice this is in joules again, and this is in kilojoules. So we're going to have to move the decimal place 3 places over. So I'm going to move that over so that we can have it in kilojoules. Okay? We're going to still use the same equation. Delta G is equal to delta H minus T delta S. And notice our temperature is already given in Kelvin. So that makes things a little bit easier, doesn't it? Okay, so let's plug in our numbers. So we have our delta H of 145 kilojoules minus our temperature of 382 Kelvin. And we have our delta S of 0.322 kilojoules per Kelvin. Notice the Kelvin drops away again. So when we calculate this out, we have 3 sig figs. Yep, 3 sig figs. So we get a delta G when we calculate this of 22.0 kilojoules. So that is positive, right? That is a positive value so that we know that this is non-spontaneous. Okay. Let's do number 9. We've got 4 examples. So why don't you take your time, go through these examples, and check them with me in just a minute. Okay? So we've got our delta H, we've got our temperature given in Kelvin, and we've got our delta S. Notice our delta S is in joules, so we're going to have to move my decimal place over 3 places for all of these. So we have negative 75.9 minus 273 multiplied by 0.138. And this is kilojoules per Kelvin. This is kilojoules as well. Okay. All right. So when we do that, we get a value for delta G is negative 114, if I can write, kilojoules. Okay. That being negative means that we are spontaneous on this one. Okay? And if we do this one, delta G minus, or is equal to delta H minus T delta S. Notice our delta S, once again, is in joules, and this is in kilojoules. So we're going to move our decimal place 3 places over. Okay? So we have negative 27.6 kilojoules for our delta H. Our temperature is in Kelvin, so we're good. 535 Kelvin. And then we're going to multiply it by negative 0.0552 kilojoules per Kelvin. Okay, our Kelvins cancel out and we're left with kilojoules. When we calculate that out, we get 1.93 kilojoules. Now that's positive. So that is non-spontaneous. Okay, let's do this next one. We have our temperature in Kelvin, so we're okay there. Kilojoules, this is joules, so we're going to move this over once again. So I have 365 kilojoules minus 388 multiplied by negative 0.0552 kilojoules per Kelvin. And that is Kelvin. Okay, so our Kelvin cancels out. Again, we're left with kilojoules, which is what we want. And we get a positive 386 kilojoules on this. Okay, so once again, positive, so this is non-spontaneous. All right, last example. So once again, we have our delta H in kilojoules. This is in joules, so we're going to move this over 3 places so we can get that in kilojoules. We have our temperature in Kelvin, so we're ready to go. So delta G is equal to delta H minus T delta S. Our delta H is 452 kilojoules minus our temperature, which is 165 Kelvin, multiplied by 0.0557 kilojoules per Kelvin. Our Kelvins cancel out. And when we do this, we get a positive 443 kilojoules for our 3 sig figs. That being positive is also non-spontaneous. Okay, so anytime we have a positive delta G, not spontaneous. Every time we have a negative delta G, it's spontaneous. So I just want you to take a look at this little chart. If I have a negative delta H, that's an exothermic reaction, spontaneous. And I have a positive delta S, that's creating more disorder. So delta G is going to always be negative regardless of the temperature. It will always be spontaneous. Okay? On the flip side, if I have a positive delta H, endothermic, not spontaneous, and a delta S, that's negative, which is putting more order into the system, also not spontaneous. Delta G is always going to be positive regardless of the temperature. It's never spontaneous at all. These two here in the middle are where temperature really is important, okay? So if I have a negative delta H, that's exothermic, that's spontaneous. But I have a negative delta S, I'm creating more order in the system, okay? Delta G can be negative or positive. This is going to be positive it is going to be spontaneous or a negative delta G at lower temperatures. So the lower the temperature, it will go spontaneous. But the higher the temperature, it will not be spontaneous. Okay? This next one's the opposite. If I have a positive delta H, meaning that I have an endothermic reaction, I have to put energy in, but I'm creating more chaos, positive entropy. Delta G can be negative or positive depending on the temperature. These are going to be spontaneous at higher temperatures. So the warmer it gets, those are going to be more spontaneous. This is just like our melting the ice dilemma that we had. All right? So I hope you understood and have a good time doing these delta G's and figuring out spontaneity. We'll see you later. Let me know if you have any questions. Bye.